we're looking right now at one-sided limits. So we're going to come at 2 here from one side only first, and then we're going to come from the other side. In fact, what we're going to do is write it as 2 with a little negative sign, meaning that we're coming this way. And then when we're coming the other way to it, the limit coming to 2 from the positive side. So that's notation you want to be aware of. So we're traveling along here to get to there, and that means we're coming along the x-axis up to 2. This is showing that 2 is not, it will, how do you say, you can't actually put 2 into whatever equation. It will make it probably dividing by 0 or something like that. But it does mean that the limit, what you get up to as you get closer and closer and closer and closer to 2, is 2. And as you get closer and closer from this way, coming from the negative, coming from the positive, coming this way, you get closer and closer to the x value 2. Okay? And I did set this up with a y because we're simply just looking at what the minus and the plus stand for here. Now, let's take a look at the next part here for 11.3. Okay, and for that, we're looking at this graph to determine, is there a limit here? Is there a limit here? Is there a limit here? So we have at -3, and at 0, and at 2. So, this is what we do. There's 3 things. First, we come towards this point coming from the positive, from the negatives, getting closer and closer, so coming up this way, and this way, and this way. And as we get closer and closer to -3, because that's where we're at here, we are getting closer and closer to 2. But we never quite reach it. And then as we come the other way, we're coming to -3 from the positives, we're getting closer and closer and closer to 2, but we don't quite reach it. But you notice that we're getting closer to 2 and we're getting closer to 2. Because these 2 exist and because they match, that means that the limit of the function is equal to 2 as you approach -3, because you could do it from both sides. So because the left and right limits both exist and they agree, therefore there really is a limit, and that limit is that number 2, so you end up with the same thing here. Now, these ones are not filled in. Let's actually look at this coming from 0. As we come closer to 0 from the negative side, it looks like here we're getting closer and closer and closer to 0. So we would put 0 here. As we're coming the other way, as we're coming closer and closer and closer to 0 from the positives, we're coming along the graph here and we're getting closer and closer to the y value of 3. We're getting closer to 3. So they both exist, but they do not agree. So therefore, the limit of f of x of this function, the limit of the function as you get closer to 0, does not exist. Does not exist. Because the left and right limits, though they exist, do not agree. Now let's look at this one over here. So you can see that if either one of them just did not exist, then you'd be done right there. They have to both exist, and then they have to agree also. So let's look at this one. As we get closer and closer to -2, the y value gets closer and closer to 1. As we come the other way, so we're coming from the negatives for this one, as we come from the positives, we get closer and closer to +2 for the x's. That means we're getting closer and closer to 1 for the positives here. So both of them, they both exist and they both agree, so therefore the limit is that number because they both exist and agree. Okay, now let's look at another example of one of them here. Determine whether this function is continuous at A. Here's the function, and the A we're using is 6, or rather the limit that we're using. So here's what we'll look at. Okay, so here's a way of doing it when you have just the function. We don't have a graph to look at. What we're going to do here is, one, we're going to figure out what the function is at A. So that means we need to put that in there. Calculate it, 42 over 1, so we get a 42. It's defined. Now we have to do this the second time. And what we're going to do here is do the limit of the function as x approaches 6. So what we're going to do here, we want that function is equal to, well, x squared plus 6 over x minus 5. So x squared plus 6 over x minus 5. Well, when you put 6 in, you get 42. As you approach 6 from either side, if you put 6 in and you approach it, and actually if we graphed it, we'd see it, we're going to actually do the same thing. 6 squared plus 6 and 6 minus 5. So we're going to get 42 again. That means here we can say the limit of x as x approaches 6 is indeed equal, so this limit is indeed equal to the function at 6, and because 42 equals 42. So this is that one, and this is that one. And that means, yes, they exist and agree. Now, let's look at another one, an alternate example. This will be B. Okay, so what we're going to say is that f of x is equal to x squared plus 8x over x squared minus 8x. And we're going to say that a is equal to 0. So let's see if it's continuous here. And the first thing to do is we find the function at that x value. So 0, 0 squared, plus 8 times 0 is 0. 0 squared minus 0. Uh-oh, we have a problem. 0 over 0. Because of the 0 in the denominator, it's undefined. And therefore doesn't exist, so we can just stop right here. Let's see if I can get a decent stop sign. Well, there, that's close enough to say decent stop sign, because it is not continuous. We don't have to figure out anything else. We already know right now as soon as it's undefined yet. Now, there's another one where we look at a piecemeal function. And let's see what happens here when we use it. Well, because it's a piecemeal one, okay, what we're going to do, or piecewise, yep, that's right, it's piecewise. Well, it's in pieces. Good enough there. When x is equal to 6, so when the function is 6, we know from what this is, from the parameters of it, that that's just 13. Then we figure out the limit when it's at 6. So that's equal to 6 squared minus 36, 6 minus 6. Okay, so what we get, oh, wait a minute, we're going to get a 0. No, but there's something we can do. Look at what I'm doing here. Oops, actually I should do it as x minus 6, x plus 6, and then x minus 6. Aha! I can factor it, which in the last section it went through that if possible you want to factor it. So what I have is x plus 6. So really what I'm looking at, so the limit as x approaches 6, if I factor it, I can find a limit. So I can say 6 plus 6, so that equals 12. So sometimes when it looks like you'd be dividing by 0, you can look and see, oh, I should have factored it, and that would allow me to get a limit. So both of these exist. Okay? So F6, here's the problem. F6 is 13, and the limit as x approaches 6 of the function is equal to 12, so they are not equal to each other. And that means it is not continuous because all the conditions were not met. Okay? So they exist, let's see, they both exist, but do not agree, so discontinuous. Continuous. There. Okay, so there's a few different ones and ways to look at it there. Okay. Now let's determine where, now, actually, those are the main things in 11.3 to look at. So let's go back and review this here. Whoops, first one. Yep. So you can look at a limit by going from both sides. That's what we're doing here on this one, where we are, from this graph, determining that at each of these points, whether there's a limit to them. Okay, so in this case, this is to find the limits. Now, we use the same idea of having to agree and exist and agree to determine whether a function is continuous. Okay? That last one, they were all discontinuous. That was obvious. But here we can determine by finding the function for a, finding the limit for a, and then seeing if they both exist and agree, and they do. In his case, they didn't, because one of them was undefined. All right? We could have factored this one as x and x minus 8, and x and x plus 8, but then we still would have had, oh, let's see, we could have factored that. Well, actually, I should probably do that since I was talking about factoring here. Here we have x and x plus 8, and here we have x and x minus 8. So the x's cancel. Now when I put 0 in here, I get 8, and I get negative 8, which means I get a negative 1. Okay? Now, when I find the limit of it, we'll find out that it's not the same, so it's not continuous. And I've run out of room here. But I wanted to emphasize the undefined part, so that's good enough for that one now. And then this one here, we're finding, is this one, where we're finding it for 6, seeing if it's continuous, and seeing that with 13 and with 12, they are not the same, therefore it's discontinuous, so they don't agree. All right. On this last one, if anyone's concerned about doing this, I will make sure, having not yet made up a test, I will still make sure that this will not be an issue. I will use something such as, so 3x plus 5 over x. And therefore, if a was put in here, it would be undefined, and then there's no issue of having to, of simplifying it. So I would instead do that. And that would give us 5 over 0, which is undefined, so we couldn't do it. Okay, so I should do that. And then there'll be no issue over it, because in this one I wasn't trying to show about doing the simplifying or reducing or factoring before doing it. I was trying to show undefined, so that's a better example to emphasize about being undefined. All right. And the last thing of all, oh, what's that? Where are we here? 3A. No, that was it. Okay, so that's in section 11.3. Not everything, of course, but the highlights of what to focus on in 11.3.